Thanks for coming. This is the Advanced Spark TensorFlow Meetup. Hope that's what you're looking for. Super excited. First of all, thank you, Grid Dynamics. Thank you, these people here. Thank you for the pizza, for the beer. This is not a cheap venue, so just please appreciate this. I've actually never spoken here at this place, so this is pretty cool. Today, it's going to be me doing the typical intro and just kind of Meetup statistics and where we're at. And then it's going to be Victoria from Grid Dynamics speaking first. And then let's see, we've got... fortunately, these guys were in town. Actually, they've been in town since last week, because last week, did you guys go home at all? Yeah, did you go home at all between last week and this week? Yeah, back to Seattle. That's a pretty light flight. So we got some guys from Google here. Very fortunate to have them. Funny story about Tyler, actually. He and I had applied to speak at the Kafka Summit, and Tyler is part of that group, right? Yeah, do you remember that? And somehow my abstract didn't make it, or my update to the abstract, I missed some deadline, and they freaked out and pulled me from the Kafka Summit, and Tyler helped renew. Tyler got me back on the roster, so I am forever indebted to him. These guys have been speaking for the last 2 weeks, basically. So this is your fifth?
This is my fifth unique talk in 7 days.
Yeah, fifth unique talk in 7 days. So pretty excited. Let's see. Yeah, Victoria's going to introduce Grid Dynamics, talk about that a little bit. What's the highlight here, Victoria? Oh yeah, the in-stream processing service. Yeah, you guys have been around since 2005, 6? Right when, like Amazon got started, right? Or the Amazon Web Services. So then we'll go into deep dive into Apache Beam. Tyler did the Ask Me Anything today, so he got pounded with a bunch of questions. Feel free to pound him more. He's been beaten down. And then we got Reuven. Is one of you going to talk about the Dataflow? Yeah. Okay, yeah, so Dataflow is the Google Cloud implementation of Beam, right? They created like an open source project, and there's a Flink runner for it, like a Flink plugin and a Spark streaming plugin, and obviously the Dataflow plugin. So, and then I'm waiting to hear back from the third talk, the Flink streaming, Jamie from Data Artisans. So yeah, his wife recently had a baby, so maybe he's with the baby. Yeah, I don't know. Okay, my quick talk here, let's see. We hit 6,000 members, actually 6,200 looks like. We've done, this is a bit inflated because I've done some conferences and we have workshops and stuff here, but I think we're at about 50 meetups worldwide, 60 meetups worldwide. So yeah, that was kind of fun to see the 3-digit thing hit there. What else? I want to give you guys a quick update. Oh yeah, we're about to hit the third largest Spark meetup. It's pretty cool. Yes, I keep an eye on this because it kind of makes me feel good, but we're about 20 people short. So if you have friends, 23 people shy of the top third spot. So yeah, email your family and friends and have them sign up, because we want to overtake. Actually, this is a really good meetup, the SF Big Analytics. They actually have the TensorFlow on Spark project for their next meetup coming up, I think, in a couple weeks or something. The guys from Yahoo released it recently, and they're bringing in the architect for that, and they'll be talking about that. So, all right, real quick update on pipeline IO stuff and what I've been working on since the last time I saw you guys. The pipeline IO repo, real quick, for those who may not know, is here. So flux capacitor is the organization pipeline. You can follow the steps here, Kubernetes on Amazon. It's basically Kubernetes based. We're focused on the serving layer, right? Serving models. And pipeline IO, so you would first install on whichever cloud you want, or you could do it locally. and then you would install Pipeline IO on Kubernetes on top of that. So this is cross-cloud, hybrid cloud, not tied to any. This is also on-premise. Yeah, you can configure it the way you want. There's a couple videos here from some recent talks that explain it. Things I've been focused on since I last spoke were a bunch of GPU stuff, which we have the GPU expert right here, Adam Gibson from SkyMind. Very happy to have him here. Yeah, he's a seasoned speaker and knows everything about GPUs. So, oh, yeah, make it larger. Yeah. What's the URL? Oh, yeah. Flux capacitor is the GitHub repo, and then pipeline. I can't seem to increase the size of the URL bar, which is probably best. Yeah, things I've been working on. I built a little command line tool. Yeah, has anyone built like a Python CLI, like a command line thing? It's so cool. I built it between last night and today, just to show you guys that I could do Python. So check this out. So let's go to a random server here. So yeah, what this is the start of, so I've been building all these components, right? Like building out this whole infrastructure, and nobody knows how to use it, right? There's a bunch of REST APIs, but people want CLIs. So let's bounce to a different server here. Make this bigger. Boom. And then, let's see, clear that. Pip install PIO-CLI. Yeah, not by accident, I've chosen prediction IO's prefix PIO. So people always confuse pipeline IO with prediction IO, which is a good thing because they got bought by Salesforce. So maybe Salesforce will send me a check by accident somehow. But so now we could just do PIO. So we can upload models, right, like to this infrastructure. It will deploy it across all the different clouds. And this is a TensorFlow model that I've got out here. It's the inception model. And let's go to an image. TensorFlow. And I'm going to classify it. It's kind of useless, but I was trying to do something fun. Because you wouldn't normally want to classify from the command line, but classify, boom. Calling out and fallback, motherfucker. Come on. There we go. All right, so here we're just passing in an image and passing in 1.jpg, whatever, and getting back the top 5. I don't know why it keeps doing the. And so similarly, or kind of, we can bounce over, look at the metrics over here. We'll see some of these things light up. Let me just launch a little load test here. We can see some of the stuff happening. So these should be blipping. Volume. Boop. Yeah. And then, of course, we've got like Prometheus set up and all the other metrics all set up as part of this here. Super tiny, I'm sorry. But yeah, so these latencies are not, this is, something weird is going on here. But it was around 200 milliseconds to classify an image. And that's actually the total time to upload the image and classify it and, get those classifications back. OK, so that's the update there. Victoria, are you ready to speak? OK. Victoria is going to talk about grid dynamics. Again, thank you, Victoria, and Grid Dynamics for the awesome food.
Well, thank you very much for having us over as sponsors. It's my pleasure to discover this meetup and this amazing community. This is our first opportunity to speak here and sponsor it, and hopefully going forward we'll be doing more things together. My name is Victoria Lifshitz. I'm a founder and these days CTO of Grid Dynamics. For those of you who never heard about us before, we're now 10, almost 11-year-old company. I've started the company back in 2006. And I was coming out of 10 year at Sun Microsystems. where I generally focused on massively distributed systems and next generation architectures. And the term cloud has not been coined yet, right? The term DevOps have not been coined yet. MapReduce has not been coined yet. Hadoop has not been coined yet. But there were clearly these new software architectures that were emerging, that were massively distributed, that were in memory, that were NoSQL, that we called computing Google style, and we called it horizontally scalable. There were no vernacular, industry vernacular for that yet, but it was clearly that it weren't your, mother's three-tier enterprise systems where everything was starting and ending with Oracle database and with a little front end in between. It was also clear that cycle time starting to matter, not computer cycle times, but developer cycle times. Amazon was already running circles around much more established retailers because they would out-innovate everybody. And even back then, Amazon could release software so much faster than anybody else. And Agile was starting to take hold, and people were starting, even big enterprises, starting to get, at least somewhat curious, if not yet serious, about shortening software development cycles. Back at those times, major software upgrades were every 2 years, right? And a minor every 6 months. Waterfall ruled, but me and a bunch of people that I work with, we were all experimenting with a lot more lighter ways of writing software services and iterating quickly and deploying and testing automatically. So these are some of the things that I've been sort of doing at Sun, way predating its mainstream times. And on top of that, the last thing that I actually formally did for Sun was I was drafted to be the architect for a very first public cloud service offering. It was called SunGrid. It launched in 2004, predating Amazon by a couple of years. It pioneered this model of selling computers $1 per CPU per hour. If somebody has been in the valley long enough, you guys might remember. So I had a chance to work on this project, and I was the architect for what was called developer utility. And the developer utility, the idea was there is a production utility and developer utility, and developers develop and test their software on your developer cloud. Cloud wasn't called a developer utility, and then you promote it to a production utility. It was an amazing collection of ideas, and I was completely sold that basically virtualization meets the internet, meets the capacity on demand, meets the cloud computing is sort of the way of the future. But boy, oh boy, were we struggling to get applications to deploy on our platform. None of the modern software stack, none of the things that companies were actually running could in any reasonable way to be deployed on this thing. So Amazon, of course, had a strike of brilliance to go after little PHP code and greenfield applications. Sun's idea of a pilot of SunGrid was to sign up, I think it was one of the giant financial services corporations for 6,000 node cluster was the idea of a pilot. No wonder that didn't work out and didn't take off. However, working on that stuff made me convinced that the future is really kind of confluence of three things. Evolution of infrastructure towards the clouds, where infrastructure will be dynamic and it will be flexible and will be charged per hour, and it will be sort of all you can eat, all you need to eat, and pay for only what you've ate, kind of a thing. Evolution of software architectures towards lightweight, massively scalable, in-memory, NoSQL, largely written with open source technologies, because open source technologies were starting to make its way, and commercial vendors had zero interest to try to figure out actually how to make it work. And the third was the agile development and what today we know as DevOps, automation, because without automation, you really could not either control dynamic fluid capacity or the software architecture stacks that now had to be composed of little tiny pieces of software. Anyhow, 2006 rolled by, and I thought this future of cloud computing will be incredibly interesting, and I wanted to create a company that would essentially focus on helping enterprises make a transition to that world. And I thought there will be a lot of customers will be interested in that help, and they will need a lot of help. That I proved to be right. And so that was kind of the genesis of the company. Now, for the last 10 years, this is basically what we've been doing. We've been taking companies on the cloud when it is open source stacks, running in a mission critical type of sort of massively scalable sort of problems, running on the clouds and with high degree automation. Now, with that territory, sort of a big data processing, transaction processing, real-time processing comes with the territory, because these tend to be the kinds of systems that we focus on. The very, very first customer of ours was PayPal back in 2006, who wanted to do fraud detection in real time, in memory, in sort of a private cloud, as opposed to big hunking Oracle system in which they were sitting on today. That's kind of the genesis of the company. And over the years, we had a fun and privilege to build big pieces of, Macy's.coms, Kohl's.coms, work with Microsoft, Cisco, Yahoo, and some of the other really, really cool companies helping them build bits and pieces of a cloud infrastructure. That's a little bit about us. Now, this is probably a very, very technical meetup. And I want to say right away that there used to be a time when I was actually a genuine engineer. This time, I'm a CTO, I'm a suit. I take credit for the work that real engineers do. So I might be a bit at the high level when you ask your questions, and I hope that you do, that go below something that I can answer myself. I have one of my engineers, Sergey, here, who are responsible for the DevOps piece of some of the things that I'll be talking about and showing. So when it comes to the deployment and DevOps, Sergey hopefully will be able to help me. I don't, unfortunately, have my colleagues who did more of the application architecture stuff. They are not even on this time zone. They're not even in this country. But anyways, we'll do the best to support your questions. If I can't answer something, I'll take it offline and follow up. OK? So I'll kind of start afar, and I'll start talking about, well, what is real time anyways? And real times can mean different things to different people. We look at it from a business application prism, and mostly focus on, well, where are big companies really spending big budgets on the new programs that have need of real-timeness. And the way I think about it is that, fundamentally, there is an event coming in. And there will be a response to this event. And we somehow want to control this event response cycle. Now, a lot of interesting things happen in between event coming in and response being formulated. One, we need to capture the event. We need to register that the event actually has occurred. Second, when event occurs, it actually augments our model of the world, because our model of the world is based on data points of everything that happened up to this point. But now a new thing has happened, right? So we actually need to go and augment our model of the world. So that's the learning piece. Well, then we want to apply our understanding of the world through whatever models we have to then analyze that event and come up with what do we want to do about it, some kind of a course of actions. And then we need to deliver that course of action, right? And here you have a response. So when we talk about real-timeness, the real questions to ask is, well, how long is the cycle? And which part of it is actually happening online versus which parts of it are happening offline? And of course, we are forever fighting for faster, shorter, better, right? So one way to try to categorize what real-time means in analytics, in machine learning, in data sciences, in AI, I kind of have this simple 3-level pyramid. The simplest thing that you can do, and this is, I think, by and large, where state of the industry is today, is that in real time, in line, you are responding to event. So event response happens in real time through some kind of online systems. But that's based on some kind of rules. But the rules are really devised offline. So the whole training learning cycle, as well as analytics cycle, it happens at best the night before, and then the results were delivered to online systems. Sometimes it can take a lot longer than a day to accumulate the latest results and then incorporate them into your new models. I'm going backwards. I need to be going forwards. OK, so the next logical step forward, and this is where stream processing engines come in, is we could do better than just respond to the event by the basically predefined, qualified rules. We can actually do analytics itself right in real time. As the events are coming in, as the events occurred, right, we want to grab them, and we want to analyze them, and we want to figure out what it is that we want to do. Learning, however, still happens offline. And the Holy Grail, Nirvana, the place where we all want to get to, is actually sort of the third step. In-stream processing technologies can get you there for some limited set of algorithms, probably not for all, because some computational problems simply don't lend itself to that degree of Leon timeliness, at least not yet. But essentially, we want to do all three things, including learning right on the fly, right? So that's kind of the world of business value with respect to real-timeness. I gave a talk a little earlier today where I focus more on kind of a business set of problems and rationalize type of business use cases and how some of them can be done with offline analytics, but some absolutely require online analytics. I'm just going to fast forward that part for more technical crowd and just briefly outline what we see today in 2017 being some of the biggest budget drivers that our customers, and a lot of them are large retailers, are allocating towards essentially real-time type of problems. And I'll start sort of reversed order. Number 6, the most obvious one, and the one that people had been using real-time system forever, are various types of alerts. Anything that is an anomaly from a normal pattern, you want to pick up and then flag and then respond. It starts with things like, of course, fraud detection. How do we know that something fishy is going on? Can you effectively monitor normal transaction flow and pick up just the ones that look odd? Surge in demand. And more clever and interesting things are related to trends or changes in weather. Can you detect those things? And if you detected those things, can you actually respond to them in any kind of interesting commercial sense? Or I will be later on showing how these systems can be used for sentiment, real-time sentiment analytics. That's our hello world demo, if you will, of the basic science kitchen that occurs for these kinds of systems. So you might want to catch the fact that public sentiments towards your brand all of a sudden suddenly shifted. Something has happened. You probably want to be alerted about this right away and figure out how to deal with it. Next is intelligent sourcing. Intelligent sourcing is a problem that a lot of retailers are starting to pick up. And that's the one that traditional technologies don't really offer a very good solution for. This is the one where, imagine that you are a major retailer, I don't know, Macy's or Kohl's. It's Black Friday. You are consuming orders at the rate of thousands, right, per hour. And you have a very complex optimizational problem to solve, which is as orders coming in and a customer is buying these 10 things, where do you ship the items from? If you do it in a silly way, and you put these 2 lines from this store and these 3 lines from this store and this 4 from that one, you're going to get absolutely killed on shipping costs, right? Your margins is going to be done. Amazon is brilliant at this, best in the industry. Everybody else sucks. And so people used to use systems that are working just fine on a much smaller scale. But with the shift more and more towards internet buying and kind of a consolidated problem of aggregated number of offers plus the number of locations, fewer and fewer retail points becomes warehouses. So now if you used to have 3 distribution centers, now you have 700 because you can ship any item from any store. All of a sudden, computationally, you can't really solve that problem the way you used to before. So you need to do this in real time, because you cannot really offload this thing. If you solve this well, you can actually start doing even smarter things, like if a customer picks some big expensive item and he's still shopping, show them only products that you can actually fulfill from the same place, right? There's actually, it might sound to the engineers like really boring business stuff, but that is a really, really hard business problems to solve with some very advanced technologies needed. So anyways, intelligent sourcing is a second class, general class of problems. Dynamic inventory management. So this is the one where we are looking at the entire supply chain, and we are trying to predict where your bottlenecks are. And if one store overstacks the supplies and the other understacks, you have incredible inefficiencies. More and more, you could do this thing on demand, and you can do it in real time, and you can reshuffle inventory, right, between your various stores and locations. But again, in order to do that, you need to do a lot of real-time, both sensory and decision-making. Dynamic pricing. Dynamic pricing is up and coming, and dynamic pricing is essentially determining a price of an item, either price of an item or the amount of discount that you're willing to give consumer who is right now buying this item, depending on a whole lot of dynamic parameters. Not only how much it's supposed to cost and what do you know about the customer and your guess as to what is the right price where you can close the deal with that guy or gal right now, and what is other competitors charging for it, and what is my total supply availability. So these kinds of things, again, are presenting very interesting business challenges that should be solved in real time. And you cannot solve it with traditional architectures. Personalized offers, and our absolutely favorite is the personalized search. We as a company do a lot of work in high-profile retail search engines. That's actually one of our specialties. We build some of the largest search engines for large item catalogs that have 100,000 to maybe million plus UPCs in a catalog, which take care of assetization and real-time availability. So this kinds of stuff is our home turf. And if you know how search engines work, it's about identifying the right fit with the right objects and then ranking them, determining relevance. And all the rage is now doing all of this dynamically and doing it completely personalized, using machine learning, and two different people searching for exactly the same phrase at exactly the same time are going to get completely different answers depending on who they are. So these are some of the set of business applications that we see very rapidly emerging, which require these kinds of architectures at a truly mission-critical scale. And it is to address largely these types of domains. We see the emerging platform of real-time analytics, of generally stream processing, or what I like to call in-stream processing, is designed to address. And one of the definite themes that I picked up at this Strata Hadoop world is everybody, it seems to be all the rage. Everybody is in streaming. Everybody is speaking and promoting real time, right? So this is, having done this now for close to 11 years, it's very gratifying to see it moving from early adopters and fringes to kind of very, very, very mainstream. Where does stream processing, if you will, fit? Well, how you manage data in the enterprise is a really, really complex landscape, right? And looking at it end to end, you have systems that collect the data that are generated by increasingly world of IoT. And you have data coming from a variety of backend systems. And you have batch processing and ETLs that collect that data sort of in mass and then transport them and transform them and index them and store them. Then you have the data lakes themselves. And then you have traditional BI and the new emerging world of data sciences. And then we tend to use it in two broad classes of applications. One are customer-facing, for online applications, and one for a back-end things that are about technical support and first response, these types of systems. Stream processing is really about this one piece. It's about how do you build real-time extensions, right, on top of that big data landscape, if you will. And one part of it is the actual stream processing, that's real-timeness, and part of it, of course, inseparable is how do you actually do data sciences, how do you actually do modeling and learning so that that stuff can work. Does that make sense? Any questions so far? Okay. So stream processing, of course, is quickly becoming mainstream, growing rapidly across multiple industries. This is just a quick snapshot subset of some of the by now almost classic applications of stream processing. But for a lot of companies, the journey really is from offline analytics to online analytics, right? A lot of companies do have Hadoop infrastructures. They do have data lakes, and they do have an awful lot of ETLs that I've already put in place over the last 5 years. And they are doing things offline. So for the companies who are doing things offline, often the conversation about stream processing or real-timeness is, well, where does it come in and what it can do better than what you already have today? And generally, we see sort of 4 big classes of problems that are well solved by adding stream processing on top of your existing big data landscape. One is real-time data ingress to essentially replace batch processing wherever possible. If you can catch event at the source just as it happens, bunch of it is coming from Internet of Things, but it could also be coming from other enterprise feeding systems. Just don't get it as a batch at the end. Get it right, maybe take it right from the message bus, because sooner or later, often these events are somehow disseminated from message buses. So don't wait, grab it right away. And then at least in your data lake, the data will always be fresh and up to the minute, and you could do your classic traditional reporting, but at least you're not waiting hours to get the data. It's always fresh, it's always there. The second large class of problems I generally call the problem of filtering or identification of actionable insight. And actionable insights are these things that are really 1 in a million. If you think about it, most of the events are uninteresting. You have a beacon that is sitting there and just reading the reads, right? And reading the reads. And only very infrequently something interesting happens that you want to pick up and say, I actually want to do something about this. So you need a very efficient means by which you can filter out all the noise from the signal and identify where is the signal. Signal is the actionable insight. Stream processing systems are very good for that. And then, of course, once you know that something is interesting, you can do one of two things. You can either farm that interesting event back to some kind of a line of business system that can take care of it, or you could just take care of it right there and now, right? So you can add then response to actionable insight right in line as soon as you identify the insight. And finally, sort of the last frontier in some sense in that pyramid of value is then starting to learn in real time and augment your models as new events occur. And sort of looking at the vendor landscape, if you will, this is the build versus buy tree. For companies who like to buy big vendor products, there is plenty of products on the market and growing very fast. Anybody who is in the Hadoop big data space either already have stream processing capabilities or adding them in a hurry. So there is a ton of products that you could choose from in that branch. But more and more companies, and those really are our customers, and I suspect most of engineers are in this meetup is probably more in the second camp. And that is, we want to build this system, but we want to build it from open components. And if you are on that train, then there is another big decision tree coming up. And I think that decision tree, a lot of people are actually not yet cognizant that they're making. They're almost making them as emergent behavior. And that is, do you want to bet on a cloud or do you want to bet on open source? And what I mean by that is that what I think most people want is they want open source componentry running on a cloud. But what's primary? And if you pick your cloud platform first, then you're presented with a plethora of APIs that cloud vendors put in front of you. And since stream processing drives a lot of computing cycles, there is clearly a war going on and will be continued to hit between Amazon, Google, Azure, and other Google players in terms of offering developers better set of APIs. Well, once you pick one of the set of APIs, you're locked in, just like you would in any other platform, to a large extent. Now, the winner is stay open with your APIs, get the best cloud offering that you can, right? And so, that train of thought gets you to open source comes first, cloud choice comes second. And thankfully, we have an incredibly vibrant ecosystem of components that allow you to build this system. Where Grid Dynamics comes into play? Well, we're a services company, so we don't have any products. What we do is we do an awful lot of complex implementations. And when we do, what we walk away with in our IP is really the best practices and the blueprints. We learned something by doing that. And then as a CTO of Grid Dynamics, one of my missions and really sort of the underpinning of our marketing programs is let's take the lessons learned from these implementations. Let's codify them in blueprints that essentially abstract the reusable part that says this technology stack shows itself really well to solve this set of business problems. Well, let's pre-integrate it together, let's document it, and let's open source it, and let's put it out there in the community for people to use. That's really what we do, what I do, my CTO office for Grid Dynamics, that's what we do. So I call them blueprints. And what I'm going to present to you today is essentially this kind of the open blueprint for stream processing. Okay? Make sense? OK, so without further ado, this is a result of the work of a very small team that works for me at Grid Dynamics. And again, this is not so much in any kind of a new innovation as it is capturing of something that we know works in the field because we implemented a number of systems with these components. And so we asked the question, if somebody wanted to start a new stream processing project, and it's a fairly general purpose stream processor, can we come up with a standard reference architecture and reference implementation? That would be maybe 50%, maybe 70%, maybe 75% there. And then people can introduce their own specific modifications on top of that. That's really the intent. We want it to be pre-integrated. We want it to be cloud ready. But in addition to that, we also want it to be cloud portable, so that cloud is a customer choice. And not only that, but the cloud choice could be changed by the customer, basically at will. And that's something that happens an awful lot with our customers as well. Just very recently, we did a major project. We launched a new search engine for a very, very large retailer. It was a 6-month effort, which is actually fast for software of that complexity. And it went as a cloud service. But the customer changed their opinion what cloud they want to launch it in 3 times in the course of a project. And last time, it happened only a few weeks before going live. And because we invest very heavily in the layer of essentially isolation of application architecture from the underlying infrastructure, we were able to recertify yet another choice of a cloud within 2 weeks. That's actually really hard to do. And there is a real business value behind it. So I'll be showing you a little bit today, what we do to achieve that. And then we want all pieces to be basically free. And then our blueprints are free as well. Now, every software architecture has to solve some kind of a bounded load problem. Every time you change the scaling factor to 10x, you usually have to completely rewrite the architecture, right? So this one is designed to be pretty darn good and suitable for pretty darn wide range of use cases, probably not all of them. Several years ago, we had an opportunity to work with Yahoo, particularly on deploying and automating some of the testing and management of their Yahoo clusters, which at the time were the largest in the world. And they were capturing some completely incredible amount of data. And architecture like that would not work for them. But they were the largest computing thing of its time, right? So this is suitable for normal range, I would say, of business applications, somewhere between 100,000 and maybe million events per second. That's more than that. You're really, really pushing it, but that's a lot. Latency, about seconds to really compute the actionable insight and what you want to do with it, and about minutes to then deliver it to whatever is the end receiver of that system, right? Pretty good reliability on commodity type of infrastructure. And generally, streaming systems look something like this. You have events coming in, so you have some kind of a messaging service that is catching the events. And then you have some kind of a streaming framework that is processing the events. And then we're discovering that you actually need 2 types of operational stores. One is more or less very fast, lightweight, in memory for reference data. And one for much more complex data structures that might be holding application state or intermediate results or something like that. And then you need to be able to deliver the results at the end to the downstream systems in a variety of different ways. So this is a general purpose architecture of, I think, any in-stream processing system. Ours made some choices. That's the value of the blueprint, right? We made some choices. So our choices is for queuing, we use Kafka. For stream processing, we use Spark streaming. For lookup store, we use Redis. And for operational store, we use Cassandra. Now, this all tends to sit on top of, often it can stay either standalone as a cloud service that is separate from any kind of a big data infrastructure, or it can sit on top of the existing Hadoop infrastructure. And then the resulting insights can either really be delivered as a set of APIs or integrated with the HDFS or some other means. Hopefully this makes sense. This is probably pretty close to what people would do today. Interestingly enough, when we started doing things like that, Kafka wasn't around, so queuing mechanisms were different. We did a lot of work in early days with Storm. So actually, early field implementations were more Storm-based, and then Spark came along. And it's not that Storm is worse or inferior, but we looked at where the biggest usage is, and there seems to be a much more vibrant community around Spark streaming. So that's really one of the main reasons why we picked that. One of the important things to think about is that once that system creates the insights, what are you going to do with them? Right? And it has to support different modalities of doing something with it. And in this case, the critical insights could be exposed to other business app on demand, essentially through some kind of a REST APIs, right? Come and get it. It could be delivered to other systems through REST APIs, so our system can go and call them and say, here you go. Or it could be pumping data back in another message queue, which others then pick out of, or it can be ingressed into some other data store. Now, it's one thing to pick up components because they functionally do the job, and it's a whole different set of questions of how do you actually now make the entire blueprint work as a platform. And what does it mean to work as a platform? It means that the whole thing should have no single points of failure. It should have automatic failover. It should have automatic data or some sort of a data replication. And you're coordinating a lot of things. You're coordinating things that are clustered in very different ways. Kafka clusters one way, Cassandra clusters another way, Spark clusters third way, right? Redis clusters yet another way. But you need to put all of these pieces together so that you have the operational blueprint. Frankly, a lot of value of what we do and the blueprints are really on that side. Because components, again, you can replace Spark streaming with Storm, but there will be implications on operationalization of that blueprint, right? And so when all is said and done, and I'm not diving into these details today unless you guys have specific questions, and then I'm happy to try. The point is to say, these are the things that we do, and there's a whole lot of details of why this choice and how it works underneath on our blog. We have a whole series of blogs dedicated to documenting these architectures and the series of choices made behind it. At the end, what we want is not a collection of software components, but the entire system that is designed to be a platform that you can take wholesale and basically start as a baseline, start building your systems on top of it. We want it to also be operationally ready, right? So it comes fully Dockerized, containerized, Dockerized. It comes, in this case, with bindings to Mesos and Marathon. We'll talk a little more about it in the next section. We are thinking about doing reference architecture with Kubernetes. And maybe native Docker ecosystem. As these technologies mature, if you will, that's definitely, and we do quite a bit of work with Kubernetes, so Kubernetes is almost no-brainer at this point in time as the alternative deployment blueprint. Now, to make it all work, we issue reference implementation. And the reference implementation now is literally a set of scripts and buttons that you can press that allows you to take this whole multi-cluster thing and then deploy it on the cloud and actually see how it works in reality. And then again, start with that as your deployment platform. And to illustrate and how would somebody use it for data sciences, then we have a reference demo. That's a real-time Twitter sentiment analytics for new movie reviews that is deployed and running inside of that in-stream processing system and helps you understand, what goes where and where do you put the models and where do you put the analytics and how do you collect and visualize results and so forth. And so with that in mind, let me talk a little bit about now the reference implementation. And again, if reference architecture is more about software stack, then reference implementation is about DevOps stack and how to automate all major functions related to management of your platform. So this is a chosen DevOps stack for a reference implementation. The choice of a cloud is AWS for no good reason other than we had to choose one, and so that one was chosen. I'll tell you in a second what it takes to deploy it on any cloud, and you'll see that tie-in to any kind of cloud is extremely minimal. The deployment unit is a Docker container. The container management is the Mesos and Marathon. Why Mesos and Marathon versus Kubernetes? We actually go to some length discussing that on our blog, mostly because when those choices were made about a year ago, Mesos Marathon seemed to be much more mature and widely used in the industry, and Kubernetes was kind of, new kid on the block, up and coming. We are considering the revision of this blueprint sometime this year. We would very likely to do it with Kubernetes this time around, but we'll see. There is a two-step to deployment process. One is kind of the bootstrapping from what I would call bare cloud infrastructure. A set of VMs is all you get from the cloud. Now that's all you've got to get going. So we use Ansibles to get the first step of bootstrapping as automated as possible. From that point on, once you grab a certain number of VMs and kind of put the brains of operation in, now you can automate the rest. And that includes a lot of orchestration, application management. That we use one tool that you guys probably have never heard of. It's called Tanami. We are using it today. It's actually a tool and technology made inside Grid Dynamics. So it's our own proprietary IP. It's a company that Grid Dynamics acquired. We are in the process of a little bit of a soul searching. Either we will open source that for a greater of the community, or we'll port this blueprint on another alternative, fully open source implementation, so that we have it as we promise, end-to-end open source. So how do you achieve cloud portability with something as complex as deploying Cassandra here, Spark here, Kafka over there, and HDFS in between? Well, it kind of boils down to very cleanly separating kind of two phases. The bootstrapping phase from the normal application environment management space. And the bootstrapping goes something like this. Step number one, and that's one manual thing that you need to do, and that is you have to choose a cloud. You sort of can't have a robot do that for you. And once you chose the cloud, you have to go and get, using whatever cloud means are available to you, first set of VMs where you're going to install your brains. So that piece of manual. After that, we actually provide you an automated Ansible scripts to grab that set of VMs and then deploy and configure Mesos Marathon cluster. And now you've got your brains. Now, once you get the brains, now you can go to phase two, and that piece could be completely automated. And that's use basically then that management cluster to provision the rest of ISP environment. And first thing you need to do is you need to bring up a bunch of different components as containers. And then you need to deploy applications. For example, one of the applications that I'll be showing uses external Twitter connections and Twitter APIs, right? So if you need to provision that, you go provision that. And some of these things could be standalone services that need to be provisioned alongside with your ISP infrastructure. Then you need to go configure all the dependencies. And after that, do fun things like scale on demand or automatically shut down an environment when you're done with it. You essentially end up with something like this. You take a bunch of VMs, and the job of Mesos, you can think about it as kind of the, it's a resource scheduler, right? It's a kernel or OS of this kind of a distributed system. And it takes VMs and treats them as a bunch of resources that it can now effectively manage. And then on top of Mesos, there will be Marathon, which is sort of a scheduler and process manager, can now take that set of VMs and now deploy processes, containers, and other things on top of that. And the end result is you would get a deployment topology of something like what you see on the left, right. hand side. And that is on top of that, the processes that are brought up and spun up are now your things like Kafka and Cassandra and Twitter feeds and that sort of stuff. Does that make sense? I know I'm going pretty fast, and there's not a whole lot of questions, but hopefully you have some questions. I'll finish in about 5 minutes, and then we could do a Q&A. So that's kind of the machinery, right? A little bit about what the pieces of the software stack is, a little bit about what the pieces of a DevOps stack is. Now let's have a little bit of fun with applications and some analytics that you can put together on top of systems like that. So to take it for a spin, I'll give you a real-time Twitter sentiment analytics for new movie reviews. We wrote this as a hello world analytics, but it quickly turned into something that is probably a bit too complex to really be considered hello world. And so we kind of think about it as a data science kitchen. And we have a series of blogs. We have, I think, 7 blog post series on Data Science Kitchen, where we document every step that data scientists would have to go through to essentially put up a sentiment analysis applications for the Twitter data. What it will do conceptually high level, it will get actual Twitter data through Twitter streaming APIs. It will apply necessary models to analyze the data in real time. So every second you actually see the new tweets coming in, and they're being sorted into positive, negative, and in various other things. And behind it, we expose all the things that make it work, which is the mathematical model, the training set, the dictionary, and the discussion for why those things were chosen for the reason they were chosen. When you have a choice of multiple dictionaries, how do you actually choose, right? What is the impact of a good dictionary or a bad dictionary? What should be the right size of the training size? And what's the relationship between dictionaries and data sets and training models and things like that? And then we give you a nice UI to then play with all that data coming back. That demo is running on AWS as a public service. Everything is open source and everything is documented. So just to give you a sense for what is it that you can do with the model is we monitor movies. And we try to have a nice mix of movies of 2016 and 2017 because it's fun to look at historic graphs. And it's fun to pick up some interesting events that happen over a long hold with some of the older movies and compare with same trends that are happening at the same time with the new movies. And sometimes you can pick up very interesting things, which are universally true of all movies. Something happens and everybody is chatting. And at other times, they're clearly chatting about one thing, but not chatting about other things. And the thing that you can't quite see, but the graph above is a real-time graph. You don't see it would say actually real-time sentiments versus historic sentiments. It's just hidden by the pop-up. But if you look at the timestamps, right? I was preparing these slides yesterday. So this is last night from 5:24 to 5:32, right? In a span of 6 minutes. This was the real data coming in and being classified. On this side, you could see the actual tweets coming. And you can click on the tweet and you'll see how it got scored, and the other way around. You can click on the scoring and we'll bring up the feeds that populated that area. Sometimes it's fascinating to troubleshoot algorithms. You look at it, well, why was this positive or why was this negative? And there is limit to what machines can do today, of course, but this is it's just fun to play with. You can look at various ways in which data is presented. And one interesting point here is that we quickly realized that not all Twitter users are born equal when it comes to influence. We have some people who are much more important, and their opinions are much more important than others. Those tend to be the ones with more followers, right? So that analytics is then further applied to 3 segments, which are all the Twitter users with less than 500 followers, between 500 and 5,000, and then the mega users, mega influencers, those who have more than 5,000 people following them. And sometimes it's interesting when the trends align or not align, right? Finally, a couple of interesting anecdotes. So this is side-by-side comparison for the same time period of Star Wars and Suicide Squad. And you can very clearly see huge peaks, right, in the distribution. So the one in December is when Carrie Fisher died. And it was interesting that we see spike in both positive and negatives. That was kind of, puzzling me for a second. I thought, well, we'll see spike of negativity. Clearly, we see that. But there was also spike of positivity. And here are some examples of the positive and negative tweets. You could see that there's a lot of uplifting things. Sometimes they're really sad messages, but a lot of them are celebratory messages. People remembering the best about career, right, of the star that passed away. Now, there on the Suicide Squad, that's an Oscar night. But what's interesting is that Star Wars did not get the spike on the same night because they weren't up for any nominations. But they got a spike in January when they announced their new Star Wars movie, right? Next movie comes in, everybody's chatting about them. So it's obvious, but these are the kinds of things that are very clear on those graphs. And I'm done with my Kant presentation. But what I want to show you is, first of all, this is this little live demo that I was talking to you about. It's a teaching tool, so it's for fun. But we explain you a little bit what it is. We give you a bunch of different links to where to read more or where to go to deploy it. And then you can go and play with this stuff. And this is real time. As you can see, this, I don't know, 11:34. Yeah, I didn't refresh it. Yeah, in a long time. So there you go. It will take a second to restart, but you see historical is right there. This is now 1912, and we're going to start seeing some, Doctor Strange, nobody is going there. We should go to Star Wars. Oh, and you could see, so this is one tweet, but then as more of them are starting to fall off, they're going to start being scored, right? The last thing that I wanted to do today is show you just a little bit of our blog. Because all of this is just a highlight, but in the blogs, we really put all the content where we document how all that stuff works under the cover. So for example, this is our blog, and we have series of blogs on big data, and some on search, and some on data sciences. We're starting to write about AI and chatbots and other fun things like that. But for example, under data sciences, we have this 7-post series on Data Science Kitchen, and it really starts with, why we're doing this, and then what is the scientist's key vocabulary and key scientific process. And then how do you understand structure of the data in Twitter strings enough to figure out what is the approach that you're going to take in creating these models. And after that, discussing, how do you construct data dictionary? Where do they come from? What constitutes good dictionary versus bad dictionary? How we ended up, we give you a list of dictionaries that we've selected here and justify and explain why. And then there is a special section on now creating training sets and training data and preparing the data for all of this. And then finally selecting model, training and evaluating. I'll just click on one of them and show you that we do actually take you step by step. This is about models, how they work, how you evaluate them, what are the different mathematics behind it, and so forth. So that's in a nutshell what we do. And I'm done with my Kant content. And if you guys have any questions, I'll be happy to try to answer them. Yes, please. Yep, we're an engineering services company.
Do you keep any of your secret sauce unpublished?
So a lot of secret sauce doesn't belong to us. They belong to our customers. Those are their private IP. So that we'll never divulge. What we do as a matter of a business model, when we solve an interesting business problem with a customer, and we think that there is a reusable lessons there, We usually not required to perform lobotomy, right, as a result of performing this project. So we learned something. And so then it's an R&D that's done on our nickel and dime to then create the right blueprint with the right pieces of software and create it from scratch from learnings. Those I intend to, with some good luck and health, to publish a lot more. We just got started. We started the blueprint program last year. We published 2 or 3 blueprints last year. And we published 28 deep content blog posts last year. I hope to publish 100 this year. I hope to roll out at least half a dozen blueprints. And we'll see how it goes. But I hope to open up as much of these kinds of IP as I can, because that's frankly our main go-to-market plan. Be the good guys that write about stuff people want to hear about, and then after that, customers really need help anyways.
Okay, follow-up.
Yes?
What's so difficult with online learning is the delay in, I could train my model with new data coming in.
Mm-hmm.
Is the delay the fact that you want to vet the data before you feed it to the model? Is that the issue?
No, it really depends. I mean, it depends on what volumes of data. It depends on what structures are underneath. I'll give you an example, for example, from search. So you take standard Lucene Solr, and the way indexing works, typically work, you almost can't help it but to write it as a batch process. To try to update indexes live on the fly as, let's say, product availability changes is actually a very difficult thing to do in a core technology. Now, we happen to do a lot of work with Lucene and Solr, and so our engineers over the years rewrote half of Lucene core to allow it to do things like that, which we did donate back to the community, and actually we are core committers to, some of our engineers are core committers to Solr Lucene and pretty well known in the community for our contributions along these lines, for example, specifically. But it really depends on a lot of things, on how well you can adjust data structures on the fly, and indexes and other things. Yes?
DPoS?
Hmm?
I mean, the next step looks like, for you guys, we're thinking about DPoS based on the Mesos and Marathon stack.
Mm-hmm.
Thoughts so far? I mean, I know it's kind of early yet.
I really don't know. We have a lot of ideas where to take it. And some of it is newest, greatest technology. Some of it is more integration points. Some of it going deeper in a domain. I'm very interested in deep learning as well as machine learning, and finding intersections around natural speech language processing that are bringing some of these best worlds together and trying to create a blueprint. Well, how do you actually do some of the applications which require those types of capabilities? Some of it is upgrading to maybe latest versions of something. One of the things we want to do is replace Redis with in-memory data grid, something like Apache Ignite, and so forth. Yes?
The Flink data store in your different architecture, Redis, Cassandra, and data.
Mm-hmm.
When do you recommend to store it Cassandra, and when do you recommend to store it?
So Cassandra for us is operational store. So when you need, there is a couple of use cases for that. One is when you need fairly complex data structures from your application domain. Let's even say catalog, right, and product data information, which is what you're going to be analyzing as you're making your decisions. You got to put it somewhere. You're probably going to put it in Cassandra. So it's a really good general purpose operational store. It's slow for some applications. Hence, you have something like in-memory data grid or something like Redis for lighter weight, faster access for simpler data. That's the reason why we have two. Although architects always have the best intentions, and then developers are always doing something else. So even our own engineers, with this nicely laid out difference between data stores, are starting to put things that logically would belong to Redis to Cassandra real fast. Why? It's easier to put everything in one place. And sometimes it's easier to integrate. For example, that particular demo where you have a real-time UI, while the framework that was used for real-time UI have native support of Cassandra. So it's really easy to dump the data in Cassandra and then visualize it, right, that way. You can drive Tableau from Cassandra. HDFS is usually for integration with other Hadoop-based systems.
You have Redis, but do you reconnect Redis when you write to Spark?
Yeah, so Redis is there for lookup data. When you need really quickly to look up something, Redis is a natural choice.
Does that really work in a big data environment when you have terabytes of data?
Reference data is usually small. Reference data is small, yeah, yeah. Maybe, black labeled IP addresses or some other things. Yes?
I have a question about the developer environment. You use so many different tools and languages to scale, but when I'm a developer, what I want to do, I want to make sure that whatever I deploy, I don't make any mistakes.
Yes.
I want to take it in, I want to test it as slow as
Yes.
production. Am I installing all this stuff?
I'm very glad that you asked, because that's a point that I would gladly make. Actually, part of the reason why we like containerization, why we like Docker, and why we bother with all of this is because you need to basically take the same blueprint, but you need to scale it radically between developer environment and production. So actually exactly same architecture, but completely boiled down to the essentials, smallest number of containers possible that can be fired up in a tiny environment is part of the pipe of the deal.
So I do have a copy of production on my development computer, right? It's a tiny one.
Yep, well, usually, yeah, some subset or mask data or something like that.
And I can run like whole set of tests to make sure that
So the blueprint today gives you a little tiny environment on AWS. The reference architecture, the things that bake in there. It differentiates, bring this environment with a scaled down version, which brings small number of containers, but still on AWS. And then you can create a much more complex topology as it moves through your pipeline. The use case that you describe is a beautiful use case. It's actually yet another thing that we would love to do, to actually give you, Seryoja, you have something to say? Get up.
Well, don't comment. But when we were developing it, we actually just used to compose on laptops, and of course,
So it works, but we did not, today it's not documented as a part of the
It's
blueprint.
document, yeah, but
So it works on a laptop.
I'll follow you up later.
Yeah, please do. Just follow up privately.
You already talked to me about it, but not about the development.
Okay. Okay, cool. I think we are running out of time, and you guys are running out of questions. Well, thank you very much for time and attention.
Are we live? All right. Oh, I'm live on the mic now.
Are you on?
Yep. All right.
Hello.
We're going to get rolling because we're kind of behind time here. I'm really tired. So, just saying. So you can all mill around and drink your beer, but I'm going to start talking and we'll have a lot of fun. So thanks for having us. I'm Tyler Akidau. I work at Google. This is Reuven Lax.
Also at Google.
And we're here at the Advanced Spark and TensorFlow meeting to talk about Apache Beam and Google Cloud Dataflow, which have really nothing to do with either of those things. So thank you all for coming. Let's see, a little bit about us. There's sort of a random timeline of us. Basically, we both worked on a lot of stuff in very similar roles for a number of years at Google related to data processing, stream processing. What do we work on? There's kind of a list of random Google things, many names of which are probably totally meaningless to you, but Millwheel, low-level stream processing system, this project we both started on originally. Flume is kind of a higher level batch and streaming API plus engine. Apache Beam is this now open source version of this high-level batch and streaming API that originally came out of Cloud Dataflow. Cloud Dataflow then is a fully managed batch and streaming processing engine running in Google's cloud. And then Windmill is kind of like the underlying actual low-level stream processing engine. So we're going to I'll talk briefly about Beam, kind of give you folks an understanding of what that is. How many of you are familiar with Apache Beam, by the way? All right, so there's at least 8 of you. And then how many of you are familiar with Cloud Dataflow, or at least have heard of it? Roughly similar number. Oddly not quite intersecting group. That's cool. So then after we talk about Beam, we'll talk a little bit about Millwheel and Cloud Dataflow and Windmill. This isn't going to be like kind of a high level, this is what Cloud Dataflow is, and you should come use it kind of a talk. Especially since Jamie's talking about Flink architecture kind of stuff after us, I think, we figured we'd kind of make it more of a deeper technical dive of sorts. Really, most of the stuff we're going to cover comes from these three papers that have been published over the last, 7 years? So we're not really covering anything terribly new here, so if you've read these, sorry, you can just leave now or whatever works for you. So we'll be 2 major sections. One last disclaimer before we get started, as we're totally winging this. We just totally threw these slides together last minute, and we haven't practiced it. Reuven saw the slides for the first time 15 minutes ago, so bear with us. Thank you for your patience, and
we
drink.
know them perfectly well.
Yes, and drink lots of beer. I'm just going to skip that slide. All right. So Apache Beam. So I'll probably do the Beam section, and then I'll hand over to Reuven, and he'll do kind of more the Millwheel Windmill section. And he feel free to chime in if you have anything you want to add, or if I say something stupid, and I'll do the same for you. So what is Apache Beam? So Beam is really 3 things, but at the highest level, it's this model and SDKs for writing data processing pipelines. So the idea is you've got these P collections, which represent massive collections of data, or potentially massive collections of data. The P stands for parallel, because you can process these in parallel. And then you apply these things called P transforms to them, which are just, these are like the maps and filters and types of transformations that you're probably fully aware of that take a collection and transform it into something else more useful, right? And so you apply a sequence, or it's sort of a DAG of these transforms to your P collections. You get new P collections out on the other side, and out comes useful data of some sort. The point for this talk, at least, that I want to make here is that when you write a Beam pipeline, it's a very logical sort of description of what your pipeline is doing. You're very specifically targeting, what am I doing to transform this data into something useful? It's not necessarily representative of what the best way is to run that pipeline under the covers, in a physical way. In contrast, not that this diagram necessarily tells you this in relation to the previous one, but when Reuven talks later about Millwheel and Windmill, these are more of a lower level type of stream processing system. So in there, when you're writing a Millwheel pipeline or a Windmill pipeline, if you could write one directly, you're very much describing nodes in a system that saying here I'm going to have a node that's going to receive RPCs, and you're going to perform some amount of logic in it, and you really build up this graph yourself very manually. And so the gain of Beam was that you could now write your pipeline in a very declarative, clear way, and the system would optimize it for you and figure out what the best way to run it was, and then actually load up this physical representation that it would then run under the covers. And that's kind of represented here. You can see, so that's roughly looks like what Beam code looks like. I think that's actually Flume code, but you write this nice high-level description of your pipeline. It's easy to maintain, easy to understand, and you run it, and it gets optimized into this physical layer under the covers. And so, for a more sort of abstract way of looking at it, you've kind of got this nice, clear sequence of operations that you write in Beam. And once you've optimized it, we're gonna squish some things together. We're gonna shuffle some things around to run it optimally and things like that. It's very similar to writing a SQL query that then gets optimized by your query optimizer and run in a way that's actually efficient. And you don't have to know all the details of how to make it run efficiently. You can just write your pipeline very clearly. I have a couple slides here on examples of optimizations. So one of those is just fusion. So this is like function composition. So if you've got 2 stages in a pipeline, C and D, that come after another, if there's no shuffling of data, no regrouping of keys or whatever, there's no reason for those to actually be 2 separate stages in the pipeline. You can fuse those together. And you get big wins on this from not having to serialize and deserialize data and make network traffic and things like that. Sibling fusion works similarly if you have 2 paths in a pipeline that are essentially separate, but there's no real reason they need to be running separately and sending RPCs and things. Combiner lifting is another example. So if you have an associative or commutative operation, like logically what you would be doing, like the example here is you got some operation A followed by a group by key. So you're grouping by some key. So maybe you're tallying up traffic to your website, and you want to see, well, what web browser are folks visiting? So you're grouping by web browser. In which case, there aren't that many web browsers, and you're going to end up with a lot of traffic for Chrome and a lot of traffic for Safari and things like that. That can actually be difficult to handle on a single machine. So if you follow that up with a sum, you're probably going to overload your machines trying to do that sum. So the manual operation you might do is, before we do the grouping, if you've got a whole bunch of Chrome events that you're going to pass down to shuffle down to a group, you might sum those up first and get a partial sum and send it downstream. So this is the kind of thing that folks would manually do before they had systems that would do these sorts of optimizations. But you can actually, if you write your pipeline in something like Beam, where you can express these and the system can tell that you have an associative and commutative operation, they can do these sorts of optimizations for you. Yes, so this is that slide I showed you before. We don't need to see that anymore. Beam vision. So as far as what Beam looks like, so I mentioned before, Beam is this core model of, the Beam model, this way of thinking about writing data processing pipelines and a set of SDKs that you can write in. The nice thing about Beam is that we really want to have clean abstractions between these. So you can come to Beam. Any SDK in Beam is going to implement this core model, sort of faithfully, as you would expect. But you can come and use it in whatever language you choose to want. And then we also provide a choice of runners. So once you've written your pipeline in a given SDK, you can choose to run it on any of the supported suite of runners. And it's up to you to sort of choose which one's right for your use case. Whether it's do you want to run on-premise or in cloud? Do you want to run open source or not? Do you want fully managed or not? These sorts of things. And then the whole set of abstractions together kind of gives you this nice clean set of APIs, both for extending things. So folks that want to come and write like a JavaScript SDK or a Scala SDK or whatever, they don't have to come and deal with the nastiness of dealing with runners or things, because everything's nicely abstracted with these sort of Beam model abstraction layers. And similarly for runners, runner writers don't have to know all the details of writing a good SDK. They just have to learn how to take this intermediate format that describes a pipeline and execute it efficiently on their pipeline. So the reality of what we actually have in Beam looks a little more like this currently. So we have a Java SDK. I guess actually technically 0.6 went out today for Apache Beam. So we have Python now in an official release as well. So there's Python and Java as far as SDKs. We have 4 supported runners: Apache Spark, Apache Flink, Google Cloud Dataflow, and Apache Apex. There's also a gear pump runner in development on a feature branch. And this bottom portion here is still kind of in development. This sort of fun runner abstraction is what's going to allow us to take literally any SDK and run it on any of the runners. So you could take the Python SDK and run it on any of the runners, even if they're Java based. It would actually allow you to mix and match the two. So that'll be cool. So that kind of comes to the end, I think. Or do I have one more slide? No, yeah. So that comes to the end of kind of the rough overview of Apache Beam. I'll hand off to Reuven now. So he's going to kind of dive into more like a lower level walkthrough of just what the underlying architecture of Millwheel was like. These are all diagrams taken from the Millwheel paper. So yeah, go for it. And
yeah, thanks,
how it
Tyler.
goes.
So Tyler focused this in our brief slides here. We don't have time to go into too much detail about what the programming model looks like. How do you write code, and what are the semantics of that? But at the end of the day, you need to take these things and actually make it run at scale, make it run with low latency, make it have the guarantees, the consistency guarantees you need. So as you mentioned before, there's some of what we've done we've already explained in a few papers. So I'm going to focus more about the streaming runner here. We have a batch runner as well, which is how we run big batch jobs. It's a different backend. So this is a little diagram from the Millwheel paper that was, I think we posted in 2010, right?
13.
13, okay. 2013.
From Java was 10.
Okay, it's hard to keep track of all the dates. At a conference off of a lake in the middle of Italy, which is not a bad place to go present a paper. And this was a simple pipeline, a sample pipeline we put together to motivate that paper. This pipeline is for an anomaly detector. So here you have an input, which is, we use an example of web searches because we're Google, so it's a natural example for us to use. Had a computation that calculated windowed counts of basically histograms per search of how often each query was happening. And then it split. We had a model calculator that calculated models of what the graph of each query looked like over time. And then we had a spike and dip detector that would always diff the recent windowed counts against the model. And if something was too far off, it would say, here's an anomaly. This was actually taken by a real system we ran at Google for many years based off of Millwheel, which was used to detect anomalies in normally stable searches. So one of the more interesting stories about this one is after Michael Jackson died, we looked back at the time in which there was a spike detected by the system on that search query, and it was within like 5 minutes of reported time of death. And we don't know how. Like, it might have been ambulance workers issuing searches on their phone. I mean, these are aggregated queries, so we can't track it down at that level. But very, very quickly afterwards, we had similar with the earthquake in Japan. This system showed anomalies in that before any news outlet had reported an earthquake. So what was the Millwheel model? The Millwheel model was a key partition model. So this actually maps very nicely to the Beam model where you do group by keys and you process things per key. Everything traveled through the system as key value pairs, actually key value timestamp pairs, because event time is a key part of the model. And the way you interfaced with it, you had a much lower level API than the Beam thing. So it's actually a little more like a MapReduce type model where you had a class and you overrode some virtual methods. In this case, a process record method and a process timer method. And every time a record came, you got this process record callback, and you do things like you could write state, or you could, for this key, or read state you had previously written for this key, set a timer, or send messages down to a downstream stage. And there was this persistent state layer that kept consistent persistent state per key in your pipeline. So, yeah, so I mean, I'm just going to go through there. So it's key partition. So what could you do when you're processing a record? Well, there was state. There's an API. So let's say you are started by key here, and a record comes in for, search query Britney Spears, which for many years used to be the canonical example. Whenever at Google we wanted to talk about some example, it was always the Britney Spears search. Because when Google first started, I think in late 90s, early 2000s, that was always the top search. Later, it stopped becoming the top search. You can write state for Britney Spears. You can read state that you have previously written for Britney Spears. And there's a very rich state API. Where you can do more than write scalar state. You can write lists of state. You can dynamically fetch stuff. And here is an example. So data's coming in. You're getting a bunch of Britney records and one Carly records. And it's coming into this first stage I mentioned, this window counter. And what is it doing? Well, the window counter is just, in this case, for every second saying, trying to calculate how many Britney searches happened in 10:59:10, 10:59:11. How many Carly searches happened in all these buckets. So essentially, we're calculating a histogram. The model calculator is also storing state. What the model calculator is doing is it's storing models, essentially graphs. In this particular case, I think it was a spline-based model to figure out, what is the normal graph of searches for Britney, because it's going to vary throughout the day. It's going to be, you're going to have more in the morning, less in the evening, maybe more. It's actually going to vary over the course of the week. You're going to have, yes?
If you have late arriving data, will you go and update this thing?
In this particular pipeline, they did not. And the reason why was because for the model calculator, this is a lossy computation. You're taking raw data and turning into these cubic spline approximations. So for late arriving data, they would have to either somehow undo this transform and then add it into the cubic splines, or they would have to store all the raw data around waiting for late arriving data. So for this particular pipeline, no. In general, for many pipelines that people actually do where they're calculating things like sums or other aggregations where it is easy to add it in, they would. So timers and watermarks. So this is also part of the model. There is so as I mentioned before, every record is tagged with a timestamp, which is the logical event timestamp for that record. The way we deal with progress in the system is there's a notion of a watermark, which is, kind of a clock that says all data, to the best of our knowledge, earlier than this time has been processed. So if you're starting to do an aggregation from 12 to 1201 and the watermark passes 1201, you can say, I can now safely do that aggregation. I don't think a bunch of data is going to show up and make my aggregation wrong. Now, as the questioner just mentioned, there are always cases in which the watermark can be wrong. Somebody is using an app on their cell phone, gets on a plane from San Francisco to London. We think that we've seen all the data for this time period. They land in London. Their phone connects to the network and dumps all the data. Suddenly our watermark was wrong. And that's why Beam actually provides some sophisticated techniques for dealing with late arriving data. But the simple model is just you assume that the watermark is accurate and there is no late arriving data. Timers are callbacks you can set per key that will trigger when the watermark passes. So for instance, for the way this windowed counter node would work in Millwheel is you would buffer data, or you would buffer counts actually, because you would do the equivalent of this combiner lifting Tyler mentioned, where you buffer partial counts for each bucket, but you would not send them downstream to the model node or to the differ node, the spike detector node, until the watermark has passed and you had a lot of confidence that there would not be much late arriving data. By the way, extension to your question, if we go back here, turns out this model calculator in this particular pipeline had a very hard time dealing with late arriving data, so they didn't. The spike detector can. So if, let's say we get some records for Britney and we're like, that's not a spike, watermarks moves on, and then later there's late arriving data, and we say, oh, now it's above the threshold. No problem dealing with late arriving data in that particular net.
Especially these days, people are not just using events in real-time processing, they're even using commerce transactions. They're even processing real-time transactions in real time.
Yes.
Right? That's where we probably need to make sure we compute data.
Right. So a canonical example for that is people who use these systems as billing pipelines. You're charging a customer based off the output of the system. You don't have the luxury of saying, oh, well, that record was delayed by 30 minutes. I'm going to drop it. Then you just lose money. And this is why Beam was very careful to provide a lot of techniques for dealing with late arriving data. So where was I? State. So timers and watermarks. And as I said, a timer is a per key callback when the watermark passes. So for Britney, I can say, let me know when the watermark passes 1201. For Carly, I can say, let me know when the watermark passes 1201, and so on. I'm not going to go into the details. This is another diagram we just copied and pasted from the paper that we wrote. But essentially, a lot of work went down to make sure that things stayed consistent. In case of the idea behind the Millwheel programming model was the user of Millwheel should not have to worry about crash consistency or any of the other hard stuff that you have to deal with distributed systems. So this is one diagram from the paper talking about some of the stuff that Millwheel does behind the scenes to make that happen. Essentially, this particular one has to do with how we keep our state consistent. So you never have a case where you have zombie writes to state. Like you start writing, an aggregation to state, then you crash, then you come back up, And now that write that was sort of half done finishes because maybe the RPC already made it into your database but hadn't completed yet, and now you write it again. So there are techniques to do that we use to deal with that. If you're interested, I would encourage you to read the Millwell paper. Now, watermarks, which I just mentioned, we have a little diagram here of showing what the watermark is. And basically, what this is showing is that at any point in time, every item of work, every record in the system has a timestamp associated with it. The watermark tries to show the lower bound of all pending work in the system ahead of you, and the best estimate of pending work that will show up in the system at your sources. So if I am this model node and ahead of me is this windowed count node, the system will track precisely all undone work all the way to the beginning of the pipeline. And then at the edge, where we're actually getting data from the outside world, there are heuristics to track. And the accuracy of those heuristics depends on your data source. Some data sources we find that we can track extremely accurately to 4 or 5 nines. So, the amount of late data was like 0.00001%. Some you just have less insight in. So one of the examples in the previous talk was a Twitter source. So like for Twitter, there's no insights in the Twitter fire hose other than what you're getting in the Twitter fire hose. So the best you would do for that would be, keep track of timestamps you've seen over the last 60 seconds and, do an estimate based off of that. Other systems, it turns out you can have more insight into what's there and build better watermarks. And then the last thing you can do from a Millwell node is a production. That is, send a record downstream to the next node. And this is actually a similar diagram from the one before. Basically, this is weak production checkpoint. It shows one of the consistency modes in Millwell. So Millwell had 2 consistency modes for productions, the weak consistency and strong consistency. And the difference between them is fairly technical. Actually, Windmill, which is what runs the Dataflow Beam runner, only supports a strong consistency mode. So this particular graph is not applicable. But
Yes.
Sorry?
Yeah. This is just Millwell. But.
Again, this has to do with how the streaming shuffle in Millwell and in Windmill can guarantee exactly once deliveries in the face of RPC failures and RPC retries. And also it also has to do with how it decouples. So if you have a chain of nodes, A shuffling to B, shuffling to C, shuffling to D, you end up, what you don't want is these chains of RPCs because what happens is any RPC fails the whole thing up. And so when you have RPC trains that are too deep, it causes huge scalability problems. So that's what this was about. Yes. Yes. So of the shuffle, of the streaming shuffle, or the state? Yes, all of this. So if you go, so first off, we go. Millwell would checkpoint to Bigtable, which is a large-scale distributed key value store. It's essentially what HBase was later based off of, and streaming Dataflow uses something similar. So this is a durable checkpointing system.
You don't use Juki, but
No. This is the checkpointing here is usually at a very high scale. So if you are calculating stuff over 1 million QPS, you're not going to want to write at that scale to Zookeeper. You're going to want a distributed store like a HBase or a Bigtable. Or you'll be finding a lot of Jerry issues about why Zookeeper won't scale. And yeah, I mean, there's a lot more to Millwell, but those are some of the key points that we, put in this slide deck.
So I think that's pretty much what we got.
Yeah.
Any
Yeah.
questions or
Yeah, one
complaints?
question, two questions.
Is this exactly one or at least one?
Exactly once.
Exactly.
Yes. Millwheel and Cloud Dataflow are both exactly once. In some cases, for some sources, it needs some extra work from the source. And for syncs, when you're writing data out of the pipeline, you also need, some syncs support exactly once better than others. Like for file writes, you can do it for exactly once. There are some syncs that ask you to provide an ID for deduplication, but then it turns out that the system itself doesn't perfectly guarantee exactly once. So all we can guarantee for that is if we write it again, we'll give you the same ID, and if the end system has forgotten that ID, there's nothing we can do about it.
We took a lot of time for parts to go to that state exactly one.
Mm-hmm.
Like you're starting with that.
Yeah, and that was actually, so going back to the history of these systems at Google, it's kind of interesting because they've evolved for a long time, actually the batch system started evolving probably 2001, I think was about the MapReduce time frame. And they evolved from sort of the learnings of trying to run these large-scale things at Google and what we needed. So like MapReduce actually started because a couple engineers were rewriting Google's indexing system, indexing the web. And they found there was a pattern that they kept reinventing this pattern over and over again for multiple parts of the indexing system. And they had the idea, why don't we just try to code up a system based off the pattern and see if anybody else wants to use it? There's an email that I saw once that was the first email they sent out about MapReduce saying, we found this pattern, we coded it up, we don't know if anybody else will find it useful, but we're just throwing it out there and let us know if you find this useful. That's how MapReduce got started. For the streaming stuff, there were a lot of different bespoke streaming solutions at Google with different guarantees and different trade-offs. What we found with exactly once is that there was a common problem people would always hit with the systems that didn't provide exactly once, and that is you start off thinking you don't need exactly once. Usually it's because you think the duplicates won't happen too often. Sometimes people would even go further, and they would look at, figure out, okay, duplicates will happen when machine crashes, and they'll look at like a month of data of how often machines crash and come out with like mathematical sounding models of why there won't be too much duplicates. Invariably, the day comes in which stuff hits the fan, everything you thought wouldn't happen didn't happen, and they get 100% duplicates that day, which they never thought would happen. And what it boils down to is it's hard to provide half of a guarantee. So it turns out if you want to guarantee that you won't have more than 1% duplicates, the easiest way to do that is to guarantee you have no duplicates. If you want to guarantee that you never lose more than 1% of your data, the easiest way to do that is to keep all your data and throw away 1% of it. It's very, very difficult to provide, half of a guarantee because the day comes, it might only happen once a year or once every 2 years, but in these big distributed environments, invariably anything that can happen will. And the amount of weird, strange failure scenarios that have happened at Google over the years sort of far exceeds anybody's imagination to imagine what these scenarios will be. So that's where we were coming from when we built Millwheel, is that we really want to move away from these systems where you were forced to run sort of a Lambda architecture, although we didn't call it a Lambda architecture back then because that term hadn't been coined yet. But where people would run a streaming best effort system to get some graphs and then another system at the end of the day to calculate the true answer, which was also a complete pain because you have to run two systems. Turns out, your semantics are slightly different, so they're always calculating slightly different things. And the other thing that would happen is people would learn to start distrusting the streaming system. Like you had this graph, and eventually consumers of this data would learn over time that the graph would sometimes vary quite a bit from the final answer at the end of the day, and people just start ignoring it. So, all these reasons are why back in 2008 or so, when we started building Millwheel, it was one of our initial focuses, is that we should be able to get accurate data out of this.
any other companies using it in production?
Cloud Dataflow, yes. There are quite a number of companies using Cloud Dataflow in production right now. Millwheel itself was a proprietary Google system, so nobody outside of Google is using Millwheel. But the system that Tyler mentioned, Windmill, which is actually a successor to Millwheel, it's kind of like the heron to Millwheel Storm. That is an internal system that's replacing Millwheel, and it is also the system that runs behind Cloud Dataflow.
So I'm just going to talk about part of this stuff. Basically, a quick intro. I'm Jamie Greer. I work at Data Artisans. Data Artisans is the company behind Apache Flink. We were some of the original creators of Flink way back 5-6 years ago at the Technical University of Berlin. A couple years ago, founded a company called Data Artisans. And Data Artisans continues to push Apache Flink forward. And there's also a distribution of Flink, a commercial distribution backed by us, QA'd, integration tested, et cetera, by us. And that is a commercial distro that you can grab, and DA is behind it. You can get 24/7, 365 support, et cetera. There will be some products around the edges also this year that'll be part of the DA platform. But basically, that's the option for a commercially backed distribution of Flink. What I want to talk about, basically, I think these guys just before me, they sort of laid some of the groundwork so that we have some background about some of this stuff. But essentially, what I really want to talk about is like more advanced applications, what I think of as advanced applications in a stream processor. So I think there's a lot of stuff about analytics around stream processing. I think there's sort of this idea that started way back almost with Storm years ago that was like, what is streaming? What's a streaming processor? It's actually, it's some like, it's map reduce, but real time, right? That's kind of like where things started. But really that's not what people are doing that I see that are interesting these days with stream processing. I think I have not a unique position, but my job at Data Artisans is basically to make sure people are successful with Flink in production. What the advantage of that is that I see loads of real-world applications being built, right? So I'm involved in projects all over the world. Many. I mean, probably I've been involved in the last year in like 40 different stream processing applications at companies in some form or another. Usually starts with some amount of consulting and support throughout the process and stuff like that. So I get to see exactly what people are actually trying to accomplish. And what I have seen time and time again is people could tell you exactly what they're trying to build. Like in English, I could explain it to you in like 2 minutes, right? I want to do this, and then I'm going to get that event, and I'm going to update this state, and I think like a programmer, and this is exactly what I want to do, and I can tell you how to do it, right? In English. And I've seen those same people. Now let's try to map that onto these higher level APIs, like windows and triggers and all these sort of primitives. Oh, how do I think about this so that it's a fold and that kind of stuff? And I think that there's a disconnect between the kinds of applications that I see over and over and over again and these APIs that are designed, I would say, more in this sort of like analytics-y way is what I'll call it. And so we've done some stuff in Flink to actually make it easier for people to just express what they want to express. And it's unleashing the power that has always been there, at least in systems like Millwheel and Flink, where you actually have a real stateful event at a time model. So you've got fault-tolerant local state. I guess it doesn't matter that it's local. That's a very efficient way to do it. But you have fault-tolerant state, and you have event at a time processing. Okay. So what I'm going to try to talk about here is the support in Flink for advanced applications, which are flexible, stateful, event-driven, right? I don't think a lot of these applications, people don't think of them as a transform over a collection. They don't think of it like that. They think of consuming events, updating data structures, and then scheduling processing for different times to happen later. Maybe when you get a watermark that says, now I know that I've seen this much data, I've got this notion of completeness, therefore I know I can compute this. Yes, I might be wrong with my watermarks, I have to deal with late data, but the idea is that The watermark tells me something about completeness and I can do something. So that's what we're going to talk about here. There's a new thing called process function, which is probably most close, like if there are some Beam people in the room, there's a newer thing in Beam called a stateful pardo, super similar. So I think, some of the reason it's now in Beam, I guess, is probably because also people are asking for like, hey, how do we just get direct access to state and build stuff where we process things event at a time? So that's what we're going to talk about. And then the second thing I'm going to talk about is there's this really neat idea that's kind of getting a little bit of traction. I did something with it at Twitter. My background is Twitter before this. And basically, there's this difference between state and storage. So you're streaming events, you're consuming event at a time, you're building data structures up. There's sort of like the mutable state, the working set, if you call it that, that you just need to do your computation. If you're doing something simple, like in analytics, group by key and count, the counts for the current window is the state, right? Eventually that stuff is finished, it doesn't mutate anymore, and that's a good time to get rid of it and put it into a database or whatever you're going to do with it. So that's what I mean by state, and that's the difference between state and storage. So queryable state is just simply, we've got this state that's in flight, it's still being mutated. I don't want to wait for an hour to be able to access it when I write it to a database when it's complete. I still want the in-flight counts, or I still want the in-flight state. So you can sort of export to the world of view on the stream processor that looks like a key value store, and you can get that state. And you can do some really cool stuff with this that's really efficient. I could talk about a few different use cases, but I'm just going to show you one. There's a bunch of others, including in analytics, where this really shines. Okay. Other features, I'm going to skip. Rescalable state in Flink is a thing, so you can scale up and down. It'll repartition your state and everything. So even though you have stateful applications, it takes care of all of that. That's new in 1.2. Skipping through this stuff really quickly. Yarn, Mesos, Docker Swarm, Kubernetes, DCOS, Amazon EMR, Google Dataproc, all of these things have Flink, or the ability Flink can run here. These Flink run on very easily now. Yarn and Mesos has pretty deep integration where it can actually talk to Yarn and Mesos and acquire resources for itself. Works really well with Docker these days. There was some stuff we did in 1.2 to make it super seamless on Docker. Kubernetes via Docker. DCOS has Flink integration, so it's almost like, click, give me a Flink cluster. Same with if you have Amazon EMR, Flink's already installed. If you have in Google Dataproc, which I don't have as much knowledge of, I think Flink is also already available. I'm going to skip this stuff because I want to get to the security. It's good. There's a lot of stuff around security in Flink 1.2 to encrypt all the communications between things, authentication with other systems. A lot of the stuff you need in the enterprise is in Flink 1.2. Okay, so I'm going to talk about this advanced event-driven applications idea. And what we're going to do is build something. I'm going to call it Flink Trade. Flink Trade TM. Here we go. We're going to consume two things. Starting positions. Some upstream system's going to decide we're going to take a position in some equity. We're going to get a message saying, hey, this is a position that we now hold as a firm. Then there's going to be a stream of quotes. Quotes are just bids. People are saying, hey, I want to buy this many shares, and I'm willing to pay this price. We're going to process some complex time-oriented trading rules. We're going to the goal of the whole system is to trade out of the positions we currently hold to our advantage if possible, right? Because we want to make money. And we're going to also provide a dashboard to traders, asset managers, et cetera, that just show what are my current holdings, what are all the positions we currently hold. And we're going to do this all as a Flink app. We're going to have a database. We're just going to have Flink. The complex rules that we're going to implement are with the following. So we only are going to make trades where the bid price is above our current ask price. That's sort of obvious. That just means someone's willing to buy it for at least what we want to sell it for. When a trade is made, we're going to increase our ask price. So basically, Chris tells me, hey man, I'll buy some Apple for $150. I'll say, great, I'll make that trade with you, but then I'm going to bump my ask price up because it sounds like people want Apple, right? So now it's $150 and 10 cents. So we're going to keep popping it up as long as people are buying, because we are looking to optimize our profits. The other thing we're going to do is that when we get one of these starting positions, we've been told, hey, we've got this position in such and such stock. It's going to have a TTL, a time to live on it, so that once we've held it for a certain amount of time, the firm's decided we only want to hold it for this amount of time, and then I want you to aggressively trade out of this. So we're willing to hold Google, no problem, we'll hold that for a long time, maybe Apple, but I don't know. Maybe if we're asked to hold some Twitter, we might want to not hold it all that long. Sorry, okay. I feel okay. Okay, so this is a diagram. What we have is what I kind of just described. These elongated cylinders are streams of data. So we have quotes coming in, and we have starting positions coming in. We have a trading engine that we're going to build, and we have output that are also the trades we're going to make. Then in the little gray box, you've basically got the state, right? That's the mutable state I've been talking about. It's sort of like all the in-flight stuff. In order to build these dashboards for traders, that's the thing we have to have access to, right? We want to see kind of in real time what are all the positions and what's happening. It's really actually a great way to understand the system's internals, because you have this view on what's actually going on inside. So that's what we're going to do. And we don't want to do just simply this, but we want to, of course, we're going to be processing a lot of data. Say it's like options tick data. There's a lot of it, right? So it's actually a pretty heavy data stream. So we're going to use a bunch of machines, and we're going to do the partitioning. So as these guys were talking about earlier, what you commonly do in stream processing is partition by key. So you got quotes, and you've got these positions. We're just going to partition by the symbol, so Apple or Google, et cetera. And the neat thing here is that there's this very natural thing that happens. You've got quotes partitioned by key, by symbol. You've got starting positions partitioned by symbol. What that means is essentially that those two, messages, quotes for Apple and starting positions for Apple will end up on the same machine. And then you've got this little state shard, right? This positions database that's local. What you do is you supernaturally, just by the nature of like partitioned stream processing, you build this like sharded distributed key value store, where each bit of it's got some shard of the data. And it just happens like very naturally. So then we could write this data to some other system at whatever rate we have to process it. If we're doing very high scale stuff, that's very onerous because you have to scale out some key value store. Or you can do this like hyper efficient local stuff. As long as you get all the data and all the queries essentially to the same place, then you can do everything super efficiently. But then the final piece would be, well, if we have to do this dashboard, it's got to be able to look up those values as well. So you have this queryable state thing in Flink now that allows you to do that. Basically, there's a client, there's some RPC behind it, that's all taken care of. It's just a simple client for you. That program can run anywhere in some other service, any Java program, Scala program, just anywhere. It's not part of the Flink cluster. And behind the scenes, it says, hey, I need the state for this key. It'll figure out where it is, go to the cluster and get it. It caches some metadata locally and things like that to make it efficient, but it just knows where to go to get the data. So it goes to the right shard and grabs it. Yeah.
So,
Uh-huh.
very smart, but one of the complexities is that there is some rules for the trading of contracts that doesn't actually break down on an individual line. They are portfolio rules.
Uh-huh.
For example, if the portfolio exceeds something,
Some global state.
below something.
Yeah.
That's a and so that tends to clash against the partitioning.
Yeah, exactly. So say you can't, so there's some other data that's not by key, basically. It's not by key.
You have portfolio
Yeah. Yeah.
constraints, which then
Right.
aggregate back some kind of a combination of
Yeah.
positions.
Exactly. So we'll see in the code that you'll see it, it's going to say stream blah, blah, blah dot key by. You can also do stream blah, blah, blah dot broadcast, and that state just goes everywhere. So as you update I know you're calculating stuff and you have to do some sort of reduce over all of it to bring it all together and you have something. Yeah, that's a little bit trickier for sure. Yeah. But you can do things like broadcast state where you need the same data everywhere. that's not naturally partitioned, but that's a little bit different than what you're saying. You're right, yeah. Okay, so we're going to build this thing in Flink. And from here to the end, we're going to look at some code and a quick demo. Let's see. And I'll go over it pretty quickly. I just kind of want to show you guys how you build this stuff in Flink. Okay, so that's actually the whole Flink job. You are going to, this is going to read from 2 sockets. It might be in a real world, it might be Kafka, or it might be HDFS, or it could be RabbitMQ. It's all kind of the same. You just get events from somewhere. In this case, it's going to be a socket. Do some parsing, handle bad data. It's just like a technique we usually use where like, okay, well, you got some bad bytes on the wire. It's nice to catch those things, and usually you shove them somewhere else so that you can look at them later. It's not super important to this demo. So this is your positions, this is your quotes, and then you have the following. Positions connected to quotes, and then you call process. This is the process function API, and here's where we're going to implement our trading engine. So if you look at that, stream, connect, it looks exactly like, this sort of diagram here that we were just talking about. 2 streams connected together, and then you've got this thing that you build that consumes data from both of those streams, and it has its own state. Okay, so that's kind of the shell of the whole Flink job, and then there's this interesting part, which is the trading engine, and it's relatively simple too. You have the positions are going to be our state. This line of code is how you say, hey, I'm going to have this position thing, which is just a case class here in Scala. Just this part is interesting. It's just a simple value class of all the stuff we want to track. You basically, what this code right here does is just registers with Flink that this is the state that we need Flink to manage, right? So that this can be managed completely fault tolerantly. This little magic line of code is what says, hey, I actually want to make this queryable from outside Flink. That's part of the queryable state API, which is newer. And that's that. Process element 1 and 2 are a little bit unfortunate names where, in like Beam, you have these nice, more like annotation-driven APIs, which I think are quite nice. But basically, this is the position stream coming in. This is the bid stream coming in. You just get one of these calls for every single event. You do whatever you want. So in this case, when we get a new position, we update the state. That's really all we need to do. And we'll come back to this timer thing. But that's how we're going to decide when it's time to more aggressively trade out of things. And the main logic is we're consuming quotes or the bids, and it's pretty straightforward. Is it a good trade? If so, make a trade, and then update our position, okay? And then, let's see. So that's kind of a really event-oriented model. Trades come in, we decide what we're going to do for that particular trade, given all the things we have, our own state, and we decide to make the trade or not. And then there's this timer idea. So these also exist in Beam. Those guys mentioned it a bit as well. Register. So what we're going to do is register as timer here. When a message comes in that says we've started a new position, it's going to tell us how long we should hold it. After that time elapses, we can schedule at some point in the future, hey, at 3 o'clock, we've decided to get out of this thing. We don't want to be in it anymore. So go ahead and trade more aggressively. And so you can see in this on timer call, you're going to say, basically, whenever the timer fires, it's time to start being more aggressive, and we're going to adjust our ask price. And every so often, if people aren't trading with us, we're going to drop our ask price and drop our ask price and drop our ask price. When we trade, we're actually going to increase our ask price and compete like that. So that's kind of a simple trading engine, but that's kind of the idea. Yeah.
So I'm trying to understand the model behind that.
Yep.
So when you go to your if statement, basically you trade, make a trade and then update. So what if you execute the first one and then die?
Which part?
So you executed make trade,
Yep.
made a trade, then you died and you didn't get to update
Yeah.
the trade, right? So now you are
Yeah.
consistent. So how is that?
Right. So if you draw a boundary around Flink and all the state it manages, you can guarantee that all of the events are applied to that state as if each message was processed exactly once. So if there's a failure, you sort of back up in the input stream, as well as return the entire computation to a previous state that's consistent with that point. On the on the boundaries of the system, like if there's a system downstream that has already consumed that trade and done something else, yes, there you can actually see duplicate messages. So the best thing is to do is outside of the boundaries of the state. So you have Flink and you have the state it manages, and then you have what goes downstream. If you do things with side effects like that, those definitely cannot be undone. Or you can build into your application a way to undo them, but Flink can't, like, you know, magically make that happen. But the best approach, if you can do it, is at the boundaries, you can make things that go downstream idempotent, if there's a way to do it. If there's not, you have to really think about it. Yeah. And there are ways. I mean, there are ways to do this. You can actually put, like, if the final result is like a database that supports transactions, you can actually like sort of like write into the transaction, and then when Flink commits its next checkpoint, you commit to the database. But you pay for latency. Yeah, there's the trade-off. But there is actually some tooling in Flink to do that. So you kind of have like a framework for doing that for transactional syncs. But again, you pay for the cost. Yep. Okay, so that's basically what we're doing. And I think from there, maybe I can just show you like a quick demo of this code running. And so let's just, I think I might actually still have the job running, but let's see. I'll just start over from 0. Let's do run our job. Oops. Run the job. And then the other thing I'm going to do is in this same window here, I'm just going to run that little, oh, I guess I didn't show you the code real quickly. This is like a little query application. This isn't part of a Flink job. This is just something I wrote using the Queryable State API, which is the external interface. Basically, you have to specify serializer for the key, serializer for the actual position data type. Here's essentially the query that says hit Flink and get the value for some key, and then wait for the result, and then we're going to print out some stuff. And that's this thing I'm going to run here in this window. And if you notice, I ran it with watch, so it's actually just going to sit there and kind of query Flink and draw, like, kind of give us a look at the state that's inside Flink right now. So let's say we're going to buy some Google. This is what we're told from upstream. Buy some Google, a lot of shares. Price we paid was $8.50, and we want to hold it for 60 seconds max. And then we're going to try to trade out of it. So now you can actually look at the positions. Let's do another one. Twitter. We don't want a lot of Twitter. And we really don't want to hold it all that long either. So, okay, so there you go. These are now the positions we're holding. And you can actually just see, essentially, Flink is acting a whole lot like a database because there's a dashboard, right? Pretty simple. You just look up by key, and there's our state. We don't have a database. We haven't deployed anything. We don't have to operationalize anything, but we have this data here that we can query. This is still, I would say that's state, not storage, though. Like, don't kind of blur the line too much. This stuff is still mutating, and after a while, this information isn't that useful. It's not storage. It's state. Okay, so now what we can do, this is now the quote stream. Let's say people come in and they're gonna give bids. So this guy is gonna be willing to buy 100 shares of Twitter at $14. Okay, we're not gonna make a trade, right? Because our current ask price is, just under $14. Well, now it is, but it wasn't a minute ago. But now we should be able to trade at $14. But I want you to notice too, here's the state updating in real time. And those TTLs have started to expire, and so now we're just like actively like, let's lower our price and see if we can get people to buy. To me, this is sort of interesting in that this is built in a stream processor, but there's not any data streaming in right now. Nonetheless, there's logic executing. We're updating our state on the back end and doing interesting business logic. So this is more of a complex event-driven application. Now we're going to go ahead and make a trade. We should see the shares of Twitter go down. We sold 100 of them. The last trade price was $14. You can see, you can see here. And if you look, if you caught the output, that's a trade that we're outputting saying, hey, we made this trade. And that just goes back onto a stream that other systems can consume. And let's say let's trade all the way out of Twitter. Someone's willing to buy the rest of it for $13.50. And boom, we're no longer holding Twitter stock. And that, in a nutshell, is the gist of it. But really, what I'm trying to get across is that we can build what I would call complex event-driven applications. It's different from analytics. Now, analytics layers on top of this stuff really easily. So Flink is super good at doing analytics. It's super good at doing group by key and count. It's got lots of support at higher level APIs for windowing, sliding windows, tumbling windows, triggers, session windows, all of that stuff. But it's all based on top of this, and we're just kind of giving that full power to the user. And I think one of the reasons that I think this is relevant is a lot of people are trying to sort out, with all these stream processors, what's the difference? And something I get asked, especially at this conference over and over and over, what's the difference between Spark streaming and Flink, right? So this is really the difference. Flink is oriented at real high scale, robust at event at a time computation. It makes it super good at analytics, but it's a much more powerful, rich model than sort of a stream is like a table, and you can group by some column and things like that. So it's just a really different approach. And this, is, in my opinion, much more flexible. It's because it's a real stream processor. It's a real event at a time model. And because it's kind of built that way from day one to be much more flexible. So in a nutshell, that's kind of what I wanted to talk about tonight. And I think, maybe open the doors for thinking about what kinds of things can we actually build with a real stream processor. And this is kind of one of those things. By the way, this is all based on real stuff. So I work on a lot of use cases. People are building systems exactly like this. There's a lot of stuff going on in finance and fintech with Flink, and so I think it's pretty obviously because it fits this sort of this model extremely well. But people are building systems exactly like this in the real world. So that's what I got. Yeah, there's a bunch of people. Yeah, so there's a lot of traction with a few different groups. So in the kind of this area, Silicon Valley, tech companies, you've got Uber doing a lot of stuff. You've got Netflix. We did stuff when I was still there at Twitter. There's some stuff still ongoing there. Who else in the Bay Area? Those are a few. What most of those people are doing, they're the people that understand streaming more deeply already. And so they've chosen Flink to roll out platforms in their company. So for example, what Netflix is working on is stream processing as a service inside Netflix for all the other groups in Netflix. So it's like the platform team. Same thing at Uber. Then beyond that, there's the people you could talk about because they've already been public is ING Bank. They're kind of looking at they've already done some stuff in production. They're thinking about how to use Flink more throughout the company. They'll be talking at Flink Forward about exactly that. Another big tech company would be Alibaba. They're huge Flink users. They've got some of the biggest Flink clusters anywhere. So they have multiple 1,000-node Flink clusters running in production. They're also doing batch processing on Flink, which is interesting. Flink was a batch processor before it was a stream processor, but no one really talks about it that much lately. What else? There's a lot going on. Yep.
What would you say are the dominant use cases for the streaming?
Stuff like I just showed you. So there's a few, okay? Machine metrics type data is obvious. And this sort of architecture where you can query the state in flight really works well. And the reason is basically because if you didn't do it that way and you wanted reasonably low latency access to the data, you've got to scale out something that you can write all that data to. But the thing is, people only want to read a tiny portion of it. The handful of dashboards that are running, looking at some particular sets of keys, is a tiny fraction of what you'd have to write, okay? So the combination of get the data from storage plus the more recent data directly from memory in Flink is a really nice combo. So there's that. That's like really bread and butter. But like I said, a lot of traction in finance and a lot of traction in like IoT type applications. Specifically, like I've been involved with a few projects that are like connected car applications for insurance companies, which they're kind of all interested in that right now. It's kind of funny if you talk to different people in the same industry and they're all building like exactly the same thing. So that's like another one that's been pretty big. But yeah.
Any online ML?
That's a good point. So there is, especially in banking, there is, and that's what ING will be talking about at Flink Forward. There's this, people, what they're doing is like serving machine learning models with Flink. So you might build the model however you build it, and in their case, they're exporting their models to PMML, and then they load them in Flink and serve them 24/7. And there's a bunch of stuff around it to make that, they've done a lot of really specific things to sort of fit their use case. But there's that I see fairly often.
Why not that versus microservices where you can have failover with a simple load balancer?
Yeah. Do you mean building sort of microservices type applications?
Well, for serving models instead.
Oh, I see. Because they're consuming high velocity event streams, and other than the fact that they happen to be doing scoring, everything else is the same. Just consume events, and like for each event, you run the model, you get a prediction, and you do whatever you do. Yeah. Yep. Anything else?
Did you have to do much work on getting the low latency processing up to par? Because you are working with JVM, right? You've got
Yeah.
body GC and everything else like that.
We have done, yeah. In Flink, there is a lot of work. There's some people, really good people involved in the project. One of them is Stefan Ewan, and that guy can work anywhere in the stack. And the networking stack in particular is really, really well written. Flink also has its own serialization stack. And in my experience, like the stuff that I built at Twitter, you're running like 3 million messages per second and just humming along, and there's like no GC. Because we manage all our own memory, we use byte buffers for everything. It's very, very well thought out. So it's really engineered to be a very efficient 24/7 type of system. It's not sort of like built for like ad hoc stuff and everything. It's designed from day one to run all the time very, very efficiently. Yep.
What about the performance when you run
A million connections, that's not the typical kind of thing you would do. So think more like you've got millions of events per second, right? But you're writing them into something like Kafka, which is like a distributed log with some number of partitions, maybe tens of partitions, or like a really big would be 100 partitions. And so you consume from all of those. But in that case, you just scale, Flink scales out wide, right? So there's Flink running on 100 nodes, maybe each one of those nodes controls one of those partitions. So the whole thing is just wide.
I saw some examples which
A million plus what?
events.
Yeah, but those aren't connections. Yeah, those aren't, so like maybe like something like this, or so these are just instances of that trading engine running on a bunch of machines, and you partition all the data by key, so it's like data parallel. And each one of these is a little state machine over some subset of the keys, right? But it doesn't imply lots of connections. There's a connection, say, from this quote stream to one trading engine. So they're each connected like, does that make sense? Yeah. So in Flink 1.2, that's the question, if I repeat it, is the queryable state highly available? Right? So is it fault tolerant? Yes. Is it highly available? No. So when there's a fault, there's some period of time while Flink recovers, which can be very quickly. Oh, I see. Yeah, so what you do, yeah. In Flink 1.2, same thing. The lifetime of that state is basically only available to query when the job is running. Now, it can be the next version of the job. It doesn't have to be the same job ID, but like the same application. So like right now, I could make a save point, stop, blow away the whole Flink cluster, and come back up, and all the state would still be there. Right, so it's not highly available during the times when the job's down, yeah. So in a future version, one of the things we're working on is just decoupling that exactly for that reason. So you can, even though your job's down, the state could still be served, exactly, yeah.
How about things on metadata on let's say I'm looking for a custom state.
Mm-hmm.
So let's say I want to display, what to do to display on this state.
What do you mean, sorry?
Let's say I'm browsing through different
Uh-huh,
codes and
uh-huh,
codes and
yep,
let's say I maintain some custom state.
uh-huh,
Two different tiers of code inside.
uh-huh.
There is no way for me to know unless I look at the code what these are the tools which are available.
So there's no way to query from the outside and say, what is all the state that's available to me? Yeah, I mean, it's new. We're working on this stuff now. So this is the first version that kind of allows you to build these kinds of architectures. But the idea is that you know the key. Yeah. Now there can be multiple pieces of state per key. Like it's just named. So it's just a name that you create. Like if you looked in the code, it said, hey, set queryable, and it gave a name.
So the ideal thing will be if I can get a metadata and a job.
Yep. Yep.
Or some API.
Yep. That allows you to kind of inspect what's even available to query.
All the expectations are more. Rather than SQL, right? That's like job.
Yep.
I should be able to see how many.
That'd be awesome. Yep. Agreed. Anybody else? Yep.
Can I ask a silly question? But, so now my point of reference is back 8, 10, 12 years ago, we could build systems like that using memory database.
Mm-hmm.
And you would position the state, and then you would maintain your trading books, basically memory, and
Mhm.
then if quotes are coming as some kind of stream,
Mhm.
you would essentially distribute it through the
Right.
And I'm sitting and trying to figure out, you're taking a streaming engine,
Mhm.
and you're making it work with kind of business applications.
Mm-hmm.
I'm trying to figure out what is it about stream semantics that makes this, let's say, better architecture for this type of applications that the memory database isn't today.
I
If
mean,
I did this on Google Space with certain TRMs or work,
Mhm.
let's say first step,
yeah.
versus pick up Flink with this, or
Yeah.
Flink services type of workload. So how would you?
I think that the answer is if what you're doing is already naturally stream processing and you're doing like stateful stream processing, which is a very, very flexible kinds of thing. You build these DAGs, you can do all kinds of interesting computations. It's sort of a very flexible computational model. And out of that, you basically get almost for free a sharded key value store. And it has these nice properties that you can actually query this with low latency. And it's cheap, right? Because you've brought all the data that needs to be joined and things like that together. So it's all local. Of course, my background is stream processing. So kind of this insight that like, look, we just built we basically have built this sharded key value store with all these nice properties. Let's just let people query it. So I think it's just coming from different angles. Yeah.
Right.
Yep. Yeah, so what I've seen, basically what people do, more or less, is just run A/B jobs, one in each data center. And whatever system's downstream from here, like if one goes down, you just look at the other one. It's simple as that. That's the most sort of common. Active. You just run the whole thing in both places. Yep. The one that you're currently looking at. Yeah, so like if A becomes unavailable, you just switch to the other DC. You should be computing the same result. Yep. Okay. Uh-huh. Okay. Yeah. Yeah, you'd have to get into a little bit into the details of like Flink's network stack. But yeah, exactly how it chooses exactly what you're going to read next. Yeah. Mm-hmm. Mm-hmm. I'm not sure I understand the question. Yep. Yep. Okay. Okay. Yep. Yep. Yeah. Oh, I see. It depends on what you mean by connect. Really, connect in what I just showed you is just a way that you can read from two input streams and do whatever you want. Exactly. There are higher level primitives in Flink that are literally like windowed joins that have much stronger semantics. And so each of those has a very specific semantic. You define windows over both streams, and you have watermarks that kind of tell you when the data is complete, according to like how much of the data you've seen so far, according to timestamps. And when both of those windows are complete, you join them. So this level of the API is consume both of these things. Things are right out of order and everything else, and you kind of know what you're actually trying to do. But the nice thing about it, based on my experience, is that you can actually build what you want to build. Yeah. So Flink is a layering of APIs. So this is kind of like almost like this API I just described, gives you the full power of Flink. Consume events, update state, and emit stuff, and schedule stuff. And then above that is like the Flink's more like Fluent API, which is like map, flat map, filter, window, tumbling window, sliding window, apply a window function, those kinds of things. And then even above that is like CEP and SQL. So it's all kind of in layers like that. So you choose the layer at which you can express what you're trying to do. Yep.
This is a bit of a curveball, but how much jumping into interface stuff have you guys seen just out there in the wild?
Like in applications?
Yeah, with Flink.
None. None that I've seen. I mean, we use rocks internally, which requires JNI, but that's it.
Okay, so the recent GitHub issue, you guys are going to integrate GitHub data to the first then. Because like the one thing we do is we manage native memory ourselves, so there's a lot of JNI going on there.
Yeah.
And then trying to interrupt that with like Flink's memory management. I was just wondering if anything else like that.
Yeah, I mean, just the closest thing would be our integration with rocks. Yep. Is that it? All right.
Thanks, JB.
Thanks for coming.
Right on.